In this video, we return to the motivating example that we started our vector valued functions unit on, and that was the idea of tracing a three-dimensional particle through space, here a spaceship, where the trajectory is defined by cos of t, sine of t, and e to the minus t. We now recognize that as a position vector over time, and we know what we can do with that in terms of representing it, sketching it, and then analyzing properties like the velocity and acceleration. First off, let's start with an analysis of the trajectory itself. Because it's in 3D, it's a little tougher to visualize, but what we can do very easily is decompose this into the x and y components. And there we see our favorite circle, the unit speed. So what we are going to see if we look down from above, a top view of the trajectory, is a particle moving around in a circle over time. In addition to that, though, we also have a z component, and that z component is following an exponential decay, e to the negative t. Now, in the previous page, we indicated that we would be starting at time 0 this time, so no negative time values allowed, but we're going to have an exponential decay for the z value starting at time 0, which is z equals 1. So z at time 0 is equal to 1. Let's draw this in a similar way to the trajectories, limiting ourselves just to the z values. So we'll call these our z-axis, and that's 0. Here we're going to have z equals 1, and then it's going to be a trajectory that goes down and down and down. We'll only have one dimension here, so it's just going to be tracing out an arc where it's decreasing over time, but it never quite reaches 0. So our z values are going to start at 1 and then go down quickly and then slow and slower and slower and slower and slower. If we combine that with, let's just say x here. Let's make this a little more interesting. If you imagine your x starts at 1, we would have something like this, a helix. We'd be going down and down and down and down and down. And if we look at a side view of that expression, a side view of that trajectory, we would see the side of a spiral helix type structure, but with an inconsistent pitch, a pitch that's getting tighter and tighter as we get closer and closer to the axis. So top view just looks like a circle. Side view, we'd see that side of a circle and then the z component decreasing and decreasing as we get closer and closer to 0, but never quite reaching the plane. So that's a fairly intricate construction of the trajectory given a relatively simple formula. So this is a very general and broad tool for defining 3D trajectories, this vector valued function idea. Of course, once we have the formulas, we have some visualization of the position over time, we can ask questions like, what's the speed of this particular spaceship at a particular moment? So of course, speed requires velocity, which is the vector quantity. And we know how to get that now. We simply take each component and differentiate it. Derivative of sine is cosine, and the derivative of the exponential is e to the minus t, and then another negative sign as the chain rule output. Speed is the magnitude of the velocity vector, and so that's the square root of each component squared added up together. So negative sine of t all squared plus cos of t all squared plus negative e to the negative t all squared. If we take a careful look at that, the negatives inside the square, what we get is square root of sine t all squared, sine squared t, plus cos squared t, and then here we end up with e to the negative t squared is the same as e to the negative 2t. And we actually don't need brackets around that. That's reasonably clear. All square rooted. Well, we can go one step further. We don't have to. This is the speed, but we also notice that sine squared plus cos squared equals 1. So our speed as a function of time is given by that expression there. At time t equals 0, we get a speed of square root of 1 plus e to the minus 2 times 0, e to the 0, square root of 1 plus 1, square root of 2 meters per second. So we now have the ability to go from a position vector valued function or parameterized space curve to velocities and speeds. We can also look further and go down to accelerations. Notice here that we'd be talking about the magnitude of the acceleration. And for whatever reason, the idea of velocity being a vector and speed being its scalar or magnitude quantity never really translated into accelerations. Accelerations we kind of use interchangeably as the magnitude or the vector. In this context, it makes sense to look at it as the vector quantity first, and then we'll talk about the magnitude as a separate operation. Recall from the last slide that the velocity we had was negative sine t and cos t and negative e to the negative t for the z component. And so our acceleration is going to be the derivative of that. We're going to take a time derivative, and we're going to get ourselves negative cos t, a negative sine t, and a double negative e to the negative t, and we're back to positive. Now this question asked about the greatest acceleration, so greatest magnitude, so we need the magnitude of the acceleration. And if we look at these ingredients, they're actually all the same as the last one. Here we had sine, cos, and an exponential, and the plus and minuses all went away because of the squared. So we'll write it out formally once just to see what the building blocks are. But we will jump to the simplified form a little more efficiently this time. Because again, we're going to have cos squared plus sine squared, and then the exponential. The cos squared and sine squared are going to give us a 1, and then the e to the negative 2t squared, or e to the negative t squared gives us e to the negative 2t. There we go. So the magnitude of the acceleration is given by this formula here. Now, you might be tempted to do some kind of optimization strategy, that kind of thing. That is certainly effective, but here we actually have enough information to answer the question now. We have t only greater than or equal to 0 in our consideration, and we know that this decreases with t. It's an exponential decay because of the negative sign there. So as t increases, then this magnitude of acceleration is going to be 1 plus something and keeps getting smaller and smaller and smaller. And so that means we should pick the smallest possible t to maximize our acceleration. And for our particular scenario here, where the smallest t that we can pick is 0, we're going to get the largest acceleration at time 0. And being very specific here, the magnitude is going to be largest in that domain. So this is conditional on that time values, the time values we're allowed to use being only greater than or equal to 0. And if it's helpful, you can tie that back to the diagram, the idea of being spun around. The spinning is always a constant acceleration of magnitude 1, whereas this particle is initially moving down fairly quickly, but then the acceleration is upwards. You can check the sign in the calculations, and it's slowing down the most quickly, that has the most upwards acceleration at the first instant that we're considering. Once it gets to a flat trajectory down here, it's not actually changing its velocity very much. There's very low acceleration. So again, it makes sense from the graphical perspective that the first time point we have is when the acceleration magnitude is going to be largest. Let's take that one step further, imagining that spiral shape again. Only this time we're going to freeze frame a little later at time 1, and we're going to follow a trajectory after that that will be a straight line. So we saw an example of this earlier in the notes. That line we're going to call L of t. And remember how we worked that in the earlier examples. It's going to be our position plus our velocity, and let's call this position 1, and times the velocity at time 1 times time. So if we work that through, how do we get our position? We have a formula for the position. How do we get the velocity? We have a formula for velocity as well. We just sub in the values. So if we sub in our position at time 1, that'll be cos of 1, sine of 1, and e to the negative 1. That's our position at the falling off time. And then we add to that our velocity vector, which we had a couple pages ago. Here we go. Negative sine cos negative e to the negative t. So negative sine of 1, cos of 1, and negative e to the negative 1. And we multiply that by time. And so that defines our trajectory. Now there's a little bit of an inconsistency here. It's worth pointing out that we use time equals 0 kind of twice here. We have time equals 0 and time equals 1 on the trajectory, on the curve. And then we essentially redefine this point here as time 0 on the L of t curve. So in that case here we had time 0 on L of t. So just be aware that you might need to rejigger the time values to define this trajectory if you wanted it in the same 0 time as the other part. But that level of detail is something we're not going to be too concerned with in this class. As a final jumping off point for this, imagine this question here. If you follow that straight line trajectory, you've got the curve, you launch at time equals 1, and you follow a straight line afterwards. This is all in the context of a three-dimensional universe. Imagine tracing this line out, maybe with a bit more angle on it. Let's pick something that looks visually a bit more interesting. If you follow that line, eventually it's going to intersect the XY plane. That would be the landing point for you after you jump off the spaceship. The question is, what is that location on the XY plane? It's something you can definitely work out using what we have on the previous page, but it's worth exploring a bit on your own.